Okay. We're running 10 minutes late, but that's okay because we've got a nice long lunch break. So I'm very happy to introduce you to Johnpierre Paglione. Johnpierre is going to tell us about the discoveries they've been making at the University of Maryland and other places in the world on this mysterious superconductor uranium ditelluride.
Okay.
Thank you. It's 45 minutes, but as you know, a lot of questions.
Yeah, good. Okay. Am I set up here?
You're set up?
Okay. All right. It's amazing, you know, we should be experts at Zoom at this point.
I know.
Okay, so I'm glad to join this meeting. It's at least today and onward. It's been a great discussion already. And so Michelle gave a great talk about the basics of qubits and so on, and now I'll go to the other extreme, talking about some novel material that we've studied for about 5 years now, and you know, with some loose connection to potentials for quantum technologies, but we have to start with the basics, right? That's the other extreme that we're discussing. I'm going to talk about uranium telluride. It's a newly discovered superconductor that's potentially a topological superconductor, and it has quite a lot of interesting aspects to it. So I thought I'd give a sort of general talk about this material and its properties, and along the way go through some of the recent work we've done and understanding we've got to in the last few years. Okay, so yeah, 5 years has been quite a long. Does not seem like a long time at all, but we've learned quite a bit about this material from the very beginning of the discovery of what we think is spin triplet superconductivity to some really interesting ground states in this material as a function of pressure and magnetic field, and several superconducting phases and so on. These are sort of the early news and results slides I showed, and then more recently, there's been a lot of, you know, sort of second generation of studies that have appeared. So in 5 years, it's been quite an amazing amount of work, you know, probably 100 papers or something, and it's been a lot of fun. And of course, you know, with second generation of studies and news pieces, you get all these, you know, amazing graphics. You know, I don't know what they mean, but they're somehow tied to this material, right? So you know, for instance, I think this is supposed to resemble some kind of actual devices or some elements that you might make from these materials. You know, and maybe we found the potential key to quantum computing. I don't know.
And AI.
Sorry?
And AI.
And AI, yes. We've solved everything. But jokes aside, you know, this is where we are at at this level. We're looking at new materials and their basic properties and just trying to understand whether we can say something definitive about the state of matter, and then think about what its implications are. And that's the challenge to make that connection to the higher levels while we're doing very basic studies. Okay, so I won't go through this in detail, but there's been several great collaborations I've connected with over the few years working on this material, in particular videos here and working on STM on this material. There's some really great stuff coming out of the lab that we've been working on with. And Brad Ramshaw flashed some ultrasound data at the very end. And several people, I'd say in my lab, probably every person is working on this material in some form or another. So starting with the discovery. Yes.
Yes. Can I ask you this question? In conjunction with earlier talk, do you see any hint of radiation?
Radiation?
Yeah.
Well, uranium is radioactive for sure.
Yeah. That's what I meant. And then anything changes with TC changes, or you know, any.
Oh no.
Hint of,
so the half-life of uranium
radiation
is billions of years. So it's not like something like plutonium superconductor where
TC changes.
where there's a radiation damage, you know, over months.
You don't
Times
see any hint of.
No, no. This is a very low level, and it's alpha particles, so it's very, very minimal. In fact, here's an antidote. Every one of you eats 1 microgram of uranium every day.
Oh, okay.
Okay.
Microgram.
Yes.
So that's
But
a
can
lot.
you,
Wow.
That's a lot.
can you grow it with different isotopes? So,
So we
We
only get access to uranium-238.
yeah,
235 is the good stuff, but that half-life is maybe an order of magnitude smaller. It's still a billion years. It's not, yeah, it's a misnomer that uranium is highly radioactive. It's not.
that's what I mean. It's not that it's radioactive.
Yeah, I understand,
Not
but
all of
I
the
want to make sure you are safe.
uranium.
It's not like the plutonium
No,
that's
you can-
glowing, you
You can
know,
work
in your
with
hand
uranium and
that you
it's
make
not-
thermoelectric
I know.
Yeah, yeah.
generators. Okay, so in any case, this is not a new material. It's an old material that was discovered, 30, 40, maybe longer, 40 years ago. But Sheng Ren, a postdoc at the time in our center in Maryland and with NIST, discovered the superconductivity in it, which was not discovered or measured previously. So that was the new result. I'm not going to go through a lot of details about the crystal growth and so on, but there's different ways to grow the crystals. And I'd say one of the nice things about this material is that there's reproducibility from different groups, several different groups around the world, growing the crystals, whether they're growing with vapor transport or flux growth or some other method, they get, for the most part, the same quality of crystals and same properties. So that has contributed to the fact that there's been so much work, outcome, 100 papers in the last several years. And that's in contrast to some other materials where there's been a lot of materials problems to try to figure out and sort of tunnel through the noise and see what's the intrinsic properties. But there is still some issues and some challenges to understanding some of the properties of this material, even at the basic level. So the crystal structure is orthorhombic, and it's intrinsically orthorhombic, meaning it's not like a tetragonal system that you stretch. It has some intrinsic orthorhombic properties, and it has these chains of uranium and tellurium atoms that I'll discuss briefly in a minute. And yeah, as I said, there's a very old work. I think this is probably one of the first papers from, I forget the year, but many years ago. Oh, 72, sorry, 1972. And even there, they commented that uranium telluride exists, very close to these other phases, other uranium tellurium phases, and that's part of the challenge that when you grow this material, you have to avoid these so-called contaminant phases. And there's a sort of window. And so this is a current challenge in the community to try to understand when you use different temperatures and so on in this growth, and you get slightly different properties, why is that? And that's, it's going to need some more detailed looks at the TEM and things like that. Yes?
Is there a relationship between these three different uranium tellurium phases? Can you kind of understand how one transforms into the other, or they're really distinct?
So UTE3 is insulating?
I just mean crystal, like their crystal structures.
Oh, they're quite different. They're quite different. So all I'll say is that there is at least one phase. I think there's a uranium-1, tellurium-1 that's cubic, and it has a lattice constant that might be close to one of the lattice constants of UTE2. So you can imagine there might be some crystal faults or something, but no one has observed anything yet. Yes, Chris,
So
and then Steve.
once your tellurium is going to have a very high vapor pressure. So is this really an effect of how much overpressure you have of tellurium? And you can shift these phases by just how much?
Yeah, that's what we thought, and we tried to do a high pressure growth, but that didn't quite work. This is a strange aspect of this material. So you can grow UTE2 in a flux of tellurium, a rich solvent, tellurium-rich crucible with 10 times tellurium to uranium, and you get crystals that are not superconducting at all. And that's, you would think that would be the ideal condition to reach the stoichiometry. And in fact, if you grow with vapor transport, if you reduce the temperature of growth, you get higher TC crystals. So it's everything the same, you just turn the knob and the TC goes up. So the stoichiometry or some kind of vacancy effect, I'm sure is playing a role. But it's not discernible in standard X-ray kind of experiments. It's at the sort of percent level, so.
But you can do single crystal X-ray and that should detect
Doesn't
even
see any
sub
difference.
1%, no?
Yes, as far as anyone has measured, there's no systematic,
Then it must be much less than that.
yeah, that's what I'm saying. At the level of a percent, there's nothing that we can see.
What about triple R?
I'll show you a slide on that.
Okay.
I just don't know the answer to this. Have people looked at the structure with XAFs or air distribution function?
Maybe, but I don't remember a
There's nothing
publication on it.
conclusive that's come out.
Yeah,
Tellurium. You know who did.
So,
Okay.
sorry,
yeah.
forgot me, you forgot.
Oh, Steve, I'm sorry.
I just, it's a really basic question. So the structure type is kind of weird. How many other materials have this structure?
None.
This is the only one.
Yes.
It's like a unicorn. Okay.
Prototype complex.
Can I add one thing there that I just think is really
Yeah.
interesting? I don't want to take over your talk. Of the ditellurides, this is like almost the only one like this.
It is the only one.
It's really unusual.
You mean only one, the superconductivity or what?
And with this crystal structure,
The crystal structure.
So ditellurides are like dichalcogenide, it's a completely different structure. Even uranium selenium too is a different structure. And let me see if I have, okay, I'll get to it later, but even if you.
Can I intervene? Can I intervene?
Henri wants to say something.
Oh,
Oh, I just do not see why you were saying that this system are reproduced very nicely. Everybody does the same with the same properties, and you are just telling us that it's not that clean.
it's not that clean. Well, that's a separate thing, but it's clean. I mean, you can make this material clean enough now that you see quantum oscillations and I would say it's a pretty good metal. It's on the order of microns.
My point is, how can you be sure now that when you compare different samples processed in different laboratories that they are identical? You were telling us that it's very reproducible. It doesn't seem to me that it is the case.
I would say that, so for instance, if I grow crystals in a vapor transport growth and change the temperature from 950 C to 850 C, I can increase TC from 1.6 to 2 Kelvin and get some, various physical properties that we measure that are nearly identical to what's done in Los Alamos or in Japan, using the same kind of parameters. Different furnaces, different materials, everything different, but roughly speaking, very similar properties. That's the reproducibility I'm talking about.
Push ahead.
There's reproducibility, but not control.
I'm gonna, as chairman, I'm gonna shut down the questions because he's gonna be localized at this view graph.
Thank you.
Let's hear a bit of the.
Yeah.
Yes, okay, so, thank you, Pierre. So the basic properties are such that it's a heavy fermion material. It has a, somewhat Curie-Weiss-like behavior at high temperatures. It seems to coalesce into some heavy fermion state at low temperatures. It's not unlike the other uranium superconductors there. The band structure was studied from the beginning, of course, and it was recognized early on that even to get a metallic state, you have to turn up the correlation strength of U in DFT calculations. Otherwise, you get an insulating state. So, that's not unusual for F electron systems. And then some RPEs and other studies have shown, and pretty conclusively now, that the the Fermi surface is composed of these quasi 1D sheets that arise from these uranium and tellurium chain structures, shown in the band structure here. So, and these are composed of these D and P states that, you know, that are not F weighted. Now, and so these give these sheets that are sort of hybridized to give you these cylindrical like shapes like that were observed. There's some aspect of a potential F weighted circular pocket that was observed in ARPES. And this has also been more recently confirmed through quantum oscillation studies, which is quite nice. And these are these lower residual resistivity samples that have been made. Ironically, at lower temperatures, that's what I was referring to, that it's kind of unusual that that's the case. So there's something non-trivial about the growth process, or something about the materials that come out of this that give you
So
lower
which
resistivity.
part of the Fermi surface are picked up by the quantum oscillations?
So they, so here's the experiment. This is, you know, the first paper by the Aoki group, and the theory mapping of the angle, and you can see it matches pretty well. So these are these cylindrical like sheets, and they're heavy. So the mass is shown here in the 30s, 40s, 50s. So these light, so at least my understanding, if I go back one, so these dispersions seen in ARPES are quite light, but ARPES probably doesn't have the resolution to see the hybridization right near the chemical potential. It's giving you the hybridized heavy states that they're actually observed in quantum oscillations. And then in passing, so Sheng's group at Washington has also claimed to observe these small pockets that have claimed to have F weight. So this is a current debate actually about whether this is.
So what you referred to theory are those what with U equal to 2, is that a DFT calculation or?
This here, yeah.
So, but then by the usual stretch of the U's that we look at is not so strongly correlated, right?
Yeah, I mean, this is what I'm saying that, okay, so you get these uranium D and P states to cross and to give you this band structure with some U. There's no F states in this band structure.
So this is DDU, right? It's a DUs.
Yes.
But there's no F
No.
U's that are
No.
coming up at least in DFT calculations.
Right.
Okay.
Correct. I mean, sorry, I forget about this particular. There may be there's I'll show another band structure later, but this is probably a calculation that uses a sort of thorium-like atom, so there's inherently no F states.
And the masses from the quantum oscillations, are they sufficiently heavy that you would say that it's got to be?
Yeah, I mean they're right here. So these are from the Lifshitz-Kossovich fits. These are 40, 50, 60 masses, and there's also a bit of a debate as to whether that completely accounts for the measured heat capacity or not, but it's pretty close.
So these masses are then F electron masses, or they from the F's or from the D's then again? Or
No, they have to be F. Yeah.
They have to be F's, right? Yeah.
So that's what I'm saying, that this band structure is composed of these P and D sheets, and this quantum oscillations measurements confirm that, but yet they're very heavy.
But you don't have F bands at the Fermi surface.
Yes. So I was
You
wondering-
You have to.
But you showed the band structure and you said that it's only the P and D bands and there's no F bands. Where are the F bands?
But it's a Kondo effect, so there's going to be a hybridization.
So-
But they have to be close to the Fermi surface to
But
hybridize.
that's, well,
Yeah, they can be close, but not cutting.
So when
the
you,
Fermi surface.
as you know, when you do DFT with F states, you usually just get a flat band that you can push away, or, even with any rare earth, for instance. So the band structure I showed is probably a thorium tellurium 2 band structure. So a hypothetical band structure with no F, no Fs. Right.
It depends on what kind of DFT they did. If they put it into the core, then the F's are gone from the beginning, right?
Okay, so I'm gonna take my power as speaker.
Yeah, you're gonna have to, because that's talking.
I'm not a DFT,
Yeah.
but just to show you, that's an important aspect, of course, where are the F states, but there's clearly heavy states there. So, and then, to make it even worse, this quasi 2D band structure you know, you might think is quasi 2D and, you know, results in quasi 2D transport or anisotropy. But in fact, you know, we measured the transport anisotropy and it's fairly 3D. I mean, in fact, the C-axis resistivity is the same magnitude as B. So there's a factor of 2 between A and B. It's B and C are about the same. But you can see right away this red curve shows quite different temperature dependence with this peak at lower temperature than A and B. So there's something unusual going on here. And, you know, I invite you to look at our paper to understand more about that. But it's speculative at this point. We don't know for sure what's going on there. Okay, so I'm going through all the controversies. So neutron scattering, there's been several inelastic neutron scattering experiments. I would say, roughly speaking, they all agree. They all give you a picture that's sort of in this top corner here, where there's intensity along the Brayton zone boundary along the B-axis. And it's so it's an incommensurate Q vector. And so this has been interpreted in different ways. One way, you know, the standard way is to think of this as an antiferromagnetic Q vector, so in sort of incipient order. My colleague Nick and our group have interpreted a slightly different way in that this is probably arising from some interband transitions to do with the band structure. But that's also occurred in debate. So the interesting thing that was observed by the Pencheng Dai's group was that in the superconducting state, at this Q vector, there's a resonance. And that's been seen in other superconductors, resonance at some Q vector. The irony is that this is a reported spin triplet superconductor. So the question immediately arose, you know, how do you get an antiferromagnetic resonance in a spin triplet superconductor, which is thought to arise from ferromagnetic interaction? And so that was also somewhat answered right away, theoretically, also in the context of strontium ruthenate, that it's possible to do that. But I would raise the question, is that even, you know, if this intensity in inelastic scattering is not to do with an antiferromagnetic interaction, then what does it mean? Yes, Steve.
So in Nick's data, I mean, you can just calculate the joint density of states since you know the Fermi surface, right? Does it match basically with what's seen in inelastic neutron scattering?
I don't remember.
Okay.
I don't remember if that's been done.
Okay.
Okay. And yeah. And so, you know, for instance, in Nick's work, they saw this dispersion sort of continue through temperature range, and it's not clear. I would say I don't believe that it's a singlet triplet excitation of the Cooper pairs giving you this resonance. But we can argue about that later. Okay, the basic properties are TC between 1.5 and 2K. The amazing thing is that the upper critical field is enormous, it's at least in the B-axis direction. First measurement was off scale, and for a 1.5 Kelvin superconductor, that's quite amazing. And I know my colleague Nick often shows this phase diagram of HC2 for different superconducters, where the Cooper rates, of course, have a huge thing. But you know, UT2 is like a delta function at 0. You know, TC is very low, and the upper critical field is enormous. And so that was studied, of course, by other groups as we progressed through this story. And so for instance, this is our data here, and it was pushed higher, and you can see that it goes all the way up to some cutoff that's believed to be a transition to a magnetic state, 35 Tesla. And sorry, let me just, sorry, this is out of order a little bit. Yeah. So that's this phase right here gets cut off. And then it was discovered by Shang at the Mag Lab that if you go off axis from B axis and crank the field up, you have a reentrant superconducting phase that pops up above 40 Tesla. And this has been studied by several groups now, confirmed, and so on. And in fact, in the latest, Nick's group has studied this in non-superconducting samples, and it's still there. It's still superconducting at 40 Tesla, even though you have no superconductivity at 0 field. So that's quite unusual, unprecedented. And what that means is the next problem to solve.
Do they have the same TC, these two different superconducting phases?
At the high field regime? Yeah, you can see here it's something like 1 Kelvin. So it's not, it's lower.
Yeah.
It's lower. And in fact, it's a bit, there's not much data about the temperature dependence of it.
And this is only seen in transport, but not in magnetization.
No, it's seen in transport, in TDO type experiments, and also magnetostriction. So there's Los Alamos work.
There's thermodynamic evidence for this superconductivity.
Yeah, so they claim the magnetostriction is consistent with a superconducting response.
Yeah, but
up and down speed.
what I'm asking, I guess, is there a quantitative estimate of how much of the sample shows that superconductivity? And is it some secondary phase that's showing up in all of these samples, or is it really intrinsic to T2?
Sorry, I don't have the data here, but if you look at, this is resistance, but if you look at TDO data, so if you go up in field and look at this field polarized state transition, the TDO data changes abruptly in the direction that you would expect for a ferromagnetic, like a magnetization increase. And in this superconducting state, it goes the other way. It looks diamagnetic.
Right, I guess I'm asking
So
how
what
much.
is the percentage? I don't know.
Yeah, that's what I'm asking. Could it be a secondary phase that's showing up in all of these
There's no
samples?
heat capacity or, there's no, hasn't been done yet as far as I know. This is pulsed field.
Yeah.
You can just reach it in Tallahassee, but it's not been done. You keep applying for MagLab time.
I want to turn you down.
Okay, if you're interested in more, there's a recent review by Nick's postdoc Sylvia, looking at all these properties in high fields. It's quite interesting. Okay, I'm sorry, I jumped around here a bit. How much time do I have? Another 10?
You have another 10 minutes.
10 minutes, all right.
And that's negotiable.
Yeah. Okay, so is it a spin triplet superconductor? For sure, or for real? That's the realistic question. So of course, the first argument is just that the upper critical field, in all directions, in fact, exceeds the Pauli limit. So that's a standard argument that Pauli limiting the singlet Cooper pair is not playing a role here. So even in the A-axis direction, where the upper critical field is between 5 and 10 Tesla, the Pauli limit is still half of that, so it's already exceeded there. But of course, NMR has been studied by a few groups, and there's been a dozen papers on NMR studies, night shift. So there's a very small change in the night shift, and this has also been a sort of a point of debate in terms of interpreting this observable change with small change in terms of what order parameter is there. And there's some experts in the audience here that can probably answer better what this all means, but I would say it's a small change. It's a matter of a few percent. So that's, even in Aoki's group, they claim this is consistent with a triplet state, and I think they might point to a fully gapped P-wave state for their interpretation. Okay, thermal transport, the studies we did early on, were also consistent with a nodal, we're consistent with a nodal order parameter symmetry in that the residual fermionic thermal conductivity at low temperatures actually goes to 0, but rises very rapidly with magnetic field and with temperature. At least consistent experimentally with several other nodal superconductors, and we've been studying that since then.
Does all of this hold with the new salt flux grown samples?
Yes. So that's, I don't remember if I chopped that part out of this talk or not, but I'll address that.
So the fully gap remark doesn't look consistent with the data shown here, or am I missing something?
Right. So there's a very, let me just see if I don't have it here, but I'll say it in words. Sorry about that. So there's a recent paper by Yuji Matsuda's group, claiming to redo this experiment on the higher TC samples and showing something that looks like this niobium curve, and claiming that it is indeed fully gapped. We're trying to finish a paper basically showing that if you go to low enough temperatures and you do your extrapolations properly, it looks very much like that, but it actually looks more like this potassium iron arsenic behavior, where there is a very, this increase with magnetic field is suppressed quite a bit, but there is a finite value and it rises pretty rapidly at low field. So it is consistent with a nodal order parameter, even the 2K.
Or something very close to that, I guess.
Something that has low energy excitations, yeah. Not fully capped. Okay, okay, so we saw an MR that, may be consistent with a gap superconductor, maybe not, but it's been triplet. Thermal conductivity that suggests there's nodes. The penetration depth that's been measured by my colleague Steve Amala in Maryland and also by the Shibayoshi group, it's fairly consistent in that they see a quadratic temperature dependence. And the important thing is that they see it in all three directions, also seen by Steve as well. And so that suggests that you have these nodal-like excitations in all directions, or at least some component. And that's been used to argue that you have not just a single set of nodes, but actually some kind of paired set of nodes that would require a multi-component sort of x plus iy order parameter. Okay, so that's the observation. And that, oh my gosh, I don't know. I came in very late, so I forgot to rearrange these slides.
We can see one of them.
That was consistent with our original interpretation of our data of heat capacity, and then collaboration with Aaron Kapitolnik, seeing a magneto-optical Kerr effect onset at TC, in that there's a splitting of TC in the heat capacity data, and there's a Kerr onset, which would be consistent with a multi-component order parameter. So meaning that there's a complex component. So that's since come under scrutiny. So here's the sort of interpretation as of maybe 2 years ago, that there's a nodal order parameter, there's a quadratic temperature dependence of penetration depth in all directions, there's a Kerr onset suggesting time reversal breaking symmetry, time reversal symmetry breaking at TC, and there's a observation of a split pair of transition temperatures. And so that would all point to a two-component order parameter. So some more recent work has emerged that suggests that may not be true, or there's some complication. So first of all, the Kerr effect was measured also by the Los Alamos group, Sean Thomas. And they're claiming not to see a Kerr effect in these zero field pool measurements. And there's some debate between these groups, which ironically, Sean was a descendant of Aaron, sort of a grandson, academic grandson of Aaron's work. So the data is fairly similar, except the Los Alamos data suggests that there's no change through TC of the Kerr effect.
Is it a different sample or is it the same sample?
So the Los Alamos group has measured, they claim to measure the same type of sample, but also the higher TC sample. So they don't see Kerr effect in any of them.
And isn't there some conversation about some samples show one transition, some show two transitions? So there's sort of correlation with Kerr effect and not, it has to do with that?
So this is the data available, and so the statement is that Aaron sees Kerr effect in the samples he studied so far, which are the two.
Which had two transitions.
TC, yeah.
And this, we don't know if it's two or one transition.
No, that one is one.
This is one.
This is one, yeah, that's right, this is one. So Los Alamos is been claiming that the two TCs are due to some sample inhomogeneity. And so I don't.
But it's not conclusive.
Well, in fact, here it is. So here's the sort of studies that have been done on these double transition. And so, for instance, here's a bunch of samples. This is measured by Priscilla Rosa and Salamos. And you can see that, for instance, there's a double transition sample here. And so they've claimed that through their thermal expansion studies and some breaking up the sample and so on, that this is just due to some separation of different TCs in the sample. We have some debates about that. And then here's the data about residual resistivity that I think someone asked about. So going from non-superconducting all the way down to the highest TCs, and you see that, you approach roughly 1,000. Between 500 and 1,000, it depends on how you define it. But, so from on the order of 1 to 2 to the order of 1,000. That's the range.
That's the molten salt flux.
Yes. I won't say how, but you don't need molten salt. We can grow crystals without molten salt. We get the same.
I get the same arrow.
Can the core effect be due to just vortex?
Yeah, so this is, okay, so you can talk to Aaron about this, or he has a follow-up paper actually, this PRD paper, which goes in depth and does sort of the first type of analysis of this beam model, critical model, to understand, when the first vortex comes in. So, so in short, so the way these experiments are done, you cool the sample in a field and then turn it off, and come up. So these are cooled in different fields, and then fields turned off, and the measurements done coming up. So as you increase the cooling field, you get a larger Kerr signal. So this is cooled in 500 Ørsted, turned off, and then it's
So you have a more vortex. So
trapped vortices. Yeah.
The vortices.
So the gist of it is that he thinks that there's just trapped vortices, and they have magnetism in the core.
Yeah, exactly. Is that the way they interpret, or no?
Yes.
Yeah, they do.
Yeah.
And so the Capitanic group is in agreement with the Los Alamos group.
Yeah. So the bottom two plots here are pretty much the same.
I thought Los Alamos didn't see Kerr.
So if you measure zero field cool, just zero field, completely zero field, and measure Kerr effect, Aaron sees an envelope, he claims, is a signature of a Kerr effect at TC.
But does he deny, has he given up on that now, or does he still?
No, he believes it.
He still believes it, I see.
Los Alamos has claimed that when they do that, this is zero field, and they use a different technique, they don't see any envelope. In fact, these dashed lines here are the envelope from Aaron's experiment, so they claim that they don't see any difference.
But this residual field is always very tricky, orthophysics.
Yeah, and there's a domain question here too. There's a domain question on.
Los Alamos will be different from California.
Let's talk later about this result.
Yeah, this is very important now.
It's really important, yes.
It is, absolutely, most critical.
Yes.
But let me give you a more definitive set of data on this question about single component. So, okay, so to add to the confusion, this is one of the earlier experiment videos with data, very nice data on STM, shows some kind of chiral states when they look at step edges. So I could give a whole talk on STM, and I won't. There's a very weak gap on the surface, and when you look at the step edges, there's a chiral kind of response in the bias in the DIDV that switches when you look at an up edge versus a down edge. And this is only in the superconducting state, and so it was claimed as evidence for some kind of chiral surface states. Again, consistent with a multi-component.
And that hasn't gone away in the flux, in the salt grown.
That has not gone away. That's correct.
Has it been measured in the salt flux ground?
Yeah, apparently.
Yes. And so to add further, the same experiment that was done to measure penetration depth, which is a microwave impedance experiment. also sees a very large residual conductivity that is associated with the surface, because we know the bulk does not have any conducting quasiparticles at these temperatures. And so one interpretation is that there's conducting surface states, and what the origin of those is a good question, but I would venture to say that they are Majorana-like excitations from the bulk order parameter gap structure. Okay, so I'll go on for that.
I'd like to make a comment about the
Sure.
surface states. And of course, I don't know anything about the surface states in uranium too, and maybe you can call me someone with a hammer that sees everything as a nail. There could be a valence transition at the surface that will produce, or it's possible to produce, conductive states on the surface that have nothing to do with topology or very little to do with topology.
Sure. So then there's many questions then. We kind of explored all these possibilities. So first question is, why don't they get proximatized? Why don't they become superconducting? So the microwave experiment sees
Because they have a
electromagnetic response of quasiparticles.
Because they have a different number of charges and they may not have the right energy for superconductivity. What I'm talking about is uranium going from, what is it in the bulk? Is it 3+?
That's a good question. It's something like 3+. Yeah.
Right, and if there is
But
another,
these phenomena are only seen below TC.
only below TC.
Only below TC.
Yeah, that's right.
Important.
And the other thing is that the penetration depth itself, the absolute number is like a micron. So it's not a, atoms at the surface kind of picture. It's this is a response.
The surface can couple with bulk, but.
Yeah, but if it's already, if the bulk is
Okay,
already
guys,
very metallic, then the contribution from the surface is gonna be small.
Okay, so let's continue this, but let me just finish.
Yeah.
So I have 2 minutes, 1 minute?
Yeah,
Let's see, because
1 minute.
it's
2 minutes plus questions.
So Brad Ramshaw compiled a nice table in his ultrasound paper, going through all the evidence for one component versus two component. And here's the answer right here, that this recent ultrasound work that we worked with him on suggests that it's actually one component. And that's not only just for the 2 Kelvin TC samples, but even the samples that show a double TC. So you can see here this solid points. This is a C33 measurement through TC. These are 2 samples, and one shows the double transition right in the data, and the other one shows the single. So the key data is actually in the shear elastic constants, where these 2 samples are measured, and you don't see any jump in the shear constants. So that puts a pretty strong constraint on whether there's a 2-component or 1-component order parameter. And the conclusion would be that it's a single component.
So is that single component state that he's proposing gapless or not?
No, it would be
nodeless or not, yeah, right.
No. So based on comparing C445566 response, he has an argument for it being B2U. I'd say that's a sort of secondary conclusion, but, meaning that the superconductivity is weakest along the Y direction, KY, so that there would be nodes along that direction. But it's not. That's right. Okay, and then finally, this is not online yet, but from Seamus Davis's group, they have some evidence of some zero bias peaks in their STM data, looking at superconductor tip tunneling, which through comparison with a theory model suggests that there is also this, well, it's a BU lower order parameter, but that there's surface and drip down states. So putting this all together, I don't have a solid conclusion, but there's a lot of hints of some interesting surface states on the material, and glad that Vidya's here so she can answer those questions.
I'm sorry.
And in the bulk, I would say that we have pretty strong evidence that there's a nodal gapped order parameter Now, I'll just end with saying that with all this about the ambient pressure superconducting state, you have to remember that, I skipped completely over the pressure dependence, but there's no ambiguity that when you apply pressure to this material, the TC splits into two TCs. And there's one TC that goes up to about 3 Kelvin and one that drops off and disappears by about 1 GPa. And there's specific heat data and there's several experiments. In fact, if you go in some regime of pressure and magnetic field, Aoki-san has shown that there's up to 4 superconducting phases. So even though there's a strong debate about this ambient pressure superconducting phase, whether it's a single component, 2 component, 2 TCs, 1 TC, all this stuff, apply some pressure and you split TCs very obviously, and there's at least 2 superconducting phases. So at ambient pressure, there's got to be some near degenerate state that's very subtle. So I don't think it's that simple to just say B2U. Okay, so I'll finish there. Thank you for all the questions.
Yeah, okay, Stuart.
So, along the B-axis, you showed the nice data showing the reentrant type behavior. My question is on the low field part of that, the low field phase. Is it thought that the destruction of superconductivity, since you're adopting this triplet picture, is vortex physics for all that low field phase? I see. So anything that occurs higher has to be a completely new state then, because you're not killing.
Yeah, I mean, my zero code response is yes, vortex physics, but the HT2 anisotropy also follows the magnetization to some degree. So maybe something more complicated, but
okay, I see. Good.
Video.
Sorry. Yeah, so the direction in which there's a node, can you tell me A, B, C, which direction is that?
so B1U is C, B2U is B, and B3U is A.
So
So B2U is a B-axis node.
nodes along
The B-axis. Remember, that's doesn't match with the penetration depth data, for instance.
So then there's no way, you're not able to reconcile these.
No, what I would say is, and I'm an ultrasound guy too, so I would take ultrasound over any of these experiments. Yeah, in that, if there was a sizable component, there should be a shear. It's just a thermodynamic relation. There should be a jump in the shear response.
Okay, and a quick clarification, the pressure studies are all isotropic pressure. So everything is squeezed at once, the entire crystal. Okay, I don't understand. That person has a question.
Thank you.
Go ahead.
So what's the rule for spin orbit coupling? For instance, polylimit, you have strong spin orbit.
Right.
So what's the rule for spin orbit coupling?
Yeah, so the poly limit I showed was for a G factor of 2. So if that's different, of course, it could be quite different. There's certainly spin orbit coupling.
But it won't get you to 40. It won't get you to 40 Tesla.
Is it?
Yeah, probably. Yeah, what would you need? I don't know, 0 point something.
Yeah, Shivaji.
Yeah, so share modules. So you don't exactly jump in C44633, it's 5. But my question is that C44, it doesn't show jump, but it doesn't show kink either.
Right.
So is there any possibility that you can somehow cancel the signal or whatever?
Yeah, good question. We don't know what's going on with C44. It's very unusual.
Because our penetration depth data is consistent with the C44 jump.
So cancels, I see. Yeah, I don't know, I haven't thought about that. But yeah. So from what I understand, is it C44? Yeah, it shows no jump, obviously that's there.
No
But
kink either. No kink either.
No, I mean, that's to the resolution of the measurement, yeah. Oh, that's a good question. I'll let the moderator, there's 5 hands up.
Look at this, and no one on this side, so let's go for it. Let's go on the left-hand side first.
In the STM image with the step edges,
Yeah.
is that effect only observed when you have a pair of opposite steps? Or if I had step up and another step up? would
Yeah,
that inversion-
I'll answer that. Yeah, it's there even if you have a step up and a step up. It's the same, as long as you know the direction of the normal to the step edge, if it's the same, if you have a series of steps with the same direction to the normal, you'll see the same thing.
And will the contrast always invert, or will it like a bright to dark, or would you have bright to brighter? Or is it inversion every time?
Contrast.
Like
You mean this contrast?
What I'm trying to figure out if it's alternating with subsequent monolayers.
No, no, there's no alternating in the which side of the Fermi energy you see these peaks. I think they're on the same side.
Yeah, let's go next one. Yeah, Alex.
In which direction do you think the point nodes are from your thermal conductivity measurements? Is that
Yeah, good question. So far, I think B, but that's a hard, so this is an orthorhombic system. So you have to account for, first of all, just the anisotropy of the crystal structure, the band structure, vortex effects, scattering. It's not easy to answer that, but if I had to give you an answer, I'd say B. So I'd say it's consistent with what Brad said about the ultrasound.
Any last questions? Yes.
Yeah, I mean, so following up on this, do we know how many nodes we have in the system? If it's really gapless?
So I don't think it's gapless.
But I think you said that it's a nodal gap.
Nodal gap, yeah, so. So Shibayuchi-san has a nice graphic here. So the question, I believe there's lots of evidence for nodal excitations. And the question then is there a single pair of nodes?
Yes.
Or is there multiple pairs? So that's a good question.
So it's not yet.
The ultrasound data suggests there's a single pair. There would be a single component, or if you have more than, if you have like the splitting here or something more exotic, then you necessitate a multi-component complex order. And I didn't say D vector at all in this discussion, but that's another degree of freedom.
Okay, let's thank JP for a great talk. So, I don't think the experimentalists have consensus on the gap, nodal, fully gap, right? If I had Yogi here, he would say it's fully gapped, right?
I don't know what he would say now.
I see. How you can say it's fully gapped if it's nodal?
He wouldn't agree with all the data.
I think if we showed him our thermal conductivity, he would not say it's fully gapped.
in Vidya's experiments also away from the images, it never looks like a hard gap. It would be because it's not. Meanwhile, the softness of the.
It's yeah, but you see.
There's a lot of density states in the STM experiment. But in the bulk, it's clearly gapped very strongly. So that's, in my opinion, that's some surface states.
It cleaves on a plane which has
That are being measured.
You don't know whether topological surface